Okay, so well, for today's seminar, we have David Obata from the Université Sergi-Pontoise. He's going to talk about uniqueness of measure of maximal entropy for the standard map.
Great, thank you. So, thank you for the invitation. I need to confess that when Lorenzo first invited me and I accepted, I didn't know how big the seminar would be. So that got me a little bit nervous. So I hope you can understand well. It's also new for me, this whole online seminar thing. So just to start with some motivation. So a general goal in dynamical systems is to understand the statistical and topological behavior of the orbits of a system. But in this generality, this usually is a hard problem, even for systems that we can consider that have some simple expression. And today, the example we're gonna look at is an example of such system. It's known as the Taylor-Shirikov standard family. And as you see in the next slide, it has a very simple expression, but we still don't understand its dynamics. There are a few things that we know, but there are many things we don't know. So to define this example, so consider the two torus as R2 quotient by Z2. And I'll put X and Y coordinates between 0 and 1. So for each real number K, the standard map with parameter K is given by the following formula. I have the X and Y coordinate, and I send this to 2x minus y plus k times 2 pi x in the first coordinate, and just x in the second coordinate. So it's a fairly simple expression. And just to give you some intuition of what's happening in the tangent level for this system, I have the following picture. So if you look at the derivative of this map, you have the following matrix. So you have a factor of 2 pi k cosine 2 pi x plus 2 in this first entry. Then you have a minus 1 and 1 here and 0. So first thing you can easily see is that this system preserves the Lebesgue measure, so the determinant is 1. And you may imagine as if k is large, as k gets large, so this entry of the matrix becomes large in a huge part of the manifold. So as long as cosine 2 pi x is not too close to 0, this entry is large for large k. So you see, what you can see is some expansion, some huge expansion happening for almost horizontal vectors in a huge part of the manifold. So that's what I'm calling the good region here in this picture. However, something very problematic can happen when you come to places where cosinus of 2 pi x gets close to 0. So this matrix, this entry of the matrix can get close to 0, and you get close to a 90 degrees rotation. And what happens is that horizontal cones, as you pass through this region, they can become vertical cones, and that makes any type of analysis of hyperbolicity for this map to become a hard thing. So you have those two small critical regions that become smaller and smaller as k goes to infinity, where you lose control of your analysis. But in a huge part of your manifold, you have this strong and good hyperbolicity happening. So because of this picture, based in many numerical analysis, it's conjecture that for large k, the standard map Fk has positive metric entropy for the Lebesgue measure. So just a comment, after Pezin's entropy formula, the positivity of the entropy for the Lebesgue measure for Fk, for the standard map, is equivalent to the existence of some region in your manifold with positive Lebesgue measure having positive Lyapunov exponents. So this conjecture is still open. We don't know about it. So in what follows, I'm gonna give talk about some non-related results for this map. So a first type of results that we can find is regarding perturbations of the standard map or some random compositions of standard map in some sense. So recently, Berger and Turaev, they proved that for large K, the standard map Sk can be infinity approximated by conservative systems having positive metric entropy. And they actually prove something more general here is as long as you have an elliptic periodic point, you can do a infinite perturbation and obtain positive entropy. Another type of result is, as I said, is if you consider random perturbations of the standard map. So you have this result by Blumenthal, Xu, and Young, where they proved that for certain random perturbations of the standard map, you get positivity of the exponent. And the random perturbations they consider is they allow some translation along the x, along the horizontal direction. And this translation is contained in some small interval. And the size of this interval depends on the parameter. So they put the uniform distribution in this interval and they consider the random product generated by translating and then applying the standard map in each step. So for these systems, they prove the positivity of the exponent. And another example that is, for me, it's, in particular, is very related with what I'm going to talk about today, is about this Beger-Carrasco example, where you can also see this as some type of adding some randomness in the system. But what you do is that you couple your standard map that you don't, so you don't understand the standard map. So you couple this with some hyperbolic base, and you consider some skew product by derived from the standard map on the fibers. And what they prove is the non-uniform hyperbolicity of this example. So it's the system they construct is a volume preserving system. And they prove that in the center direction have a positive and a negative exponent. And in a related work, I proved that their example is actually C2 robust stably ergodic. And in a certain way, what I'm going to talk about today, it goes in the sense of, okay, we don't understand the standard map, so we create this other example that it's easier to analyze. Then you try to understand some strategies that come from this other example. And then you ask the question, okay, what does it teach us about the standard map? And in a certain way, this goes in this direction, that what did we learn from the Beger-Carrasco example that can tell us something new about the standard map? So for the standard map itself, as far as I know, you can find mostly two types of results in the theory. Results for small parameters and results for large parameters. So I'm going to focus on the large parameters part. But just to mention is that because for small parameters, what is interesting is that for k equals 0, the standard map is completely integral. So you might try to understand, so this gives you a good toy model to try to understand Km type of phenomena as you change the parameter a little bit. So you have results by Gelfreit, Lazutkin, and Mackey, Mas, Percival on this sense for small parameters. But in the other part, so for large parameters, in particular for generic large parameters, there are some results. So in particular, there are results regarding the existence of some large uniformly hyperbolic sets in the manifold that are accumulated by elliptic islands. So this first result of this kind you can find in Pedro Duarte's thesis in 1994 that he also mentioned in his talk here at Resistencia Dinamica. And then there's also related results by Gorodetsky and Jacopo Simoi. And the thing is that you have this large in dimension, in Hausdorff dimension, in density, and other things, these large uniformly hyperbolic sets that are accumulated by these KM regions, these elliptic islands. And this gives a very good picture of why the standard map is hard to study, because you have these hyperbolic parts being accumulated by these elliptic parts. Um, and another result that you can also find for large generic parameters, it's a recent result by Mateus, Moreira, and Pallis, where they prove that for a generic large parameter, there exists some non-uniformly hyperbolic horseshoe. So I'm not going to define what a non-uniformly hyperbolic horseshoe is, but for those that watch the Jacques' birthday conference, that's exactly the same thing that Henrique explained very well in his talk that was introduced in the last paper of Pallis Jacques. So I'm going to focus in the second part on large parameters. And the idea is, what more can we say about the standard map for large parameters? So for that, let me just define measures of maximal entropy. So given a diffeomorphism on a compact manifold, I'm going to denote by PE of F the set of ergodic probability measures of F. And the variational principles tell us that the topological entropy of F can be achieved, or is achieved, by the supremum of the metric entropy over the ergodic measures. And a measure of maximal entropy for me, so I'm only going to be focusing on ergodic measures of maximal entropy. So a measure of maximal entropy for me is, not for me, but it is a measure that achieves the supremum. So regarding measures of maximum entropy, there is a huge literature that you can find. There are many results regarding existence and finiteness or uniqueness of these measures. And I'm not going to go through that, but I'm going to mention a few results that are more related with what I'm going to talk about today. So first, and that's a very general result by Newhouse, that states that any infinity diffeomorphism on a compact manifold has a measure of maximal entropy. And this result is based on what is known nowadays as Yonzin's theory. And in the same paper, he asked the question that is the number of ergodic measures of maximal entropy finite for a surface diffeomorphism with positive topological entropy? So some related results for these questions, you have this very strong result by Sarig in 2012 that states that C1 plus alpha surface diffeomorphism with positive topological entropy has at most countably many ergodic measures of maximal entropy. And I mentioned this result separately because in these papers, that's when Sarig introduces this very strong tool of coding that Yuri spoke very well a couple weeks ago. And more recently, Bouzy, Crovizier, and Sarig, they proved that infinity surface diffeomorphism with positive topological entropy has finitely many ergodic measures of maximal entropy. So it gives a positive answer to the question of Newhouse in the infinity category. And furthermore, if you have another dynamical condition called topological transitivity, this implies uniqueness of the measure of maximal entropy. Just as a small advertisement, so if you're interested in this result, Jérôme Bouzy, he gave a course this first semester, and it was a very nice course, and he wrote down some lecture notes that explains the proof of this theorem. You can find in his webpage. And a remark, as we saw before, since there are these elliptic islands for the standard map, in particular, there will be some invariant open regions, some open disks. So in particular, for a generic large parameter K, the standard map is not topological transitive, so you cannot apply the second part of the result of Bouzy, Crovizier, Sarig to conclude uniqueness. But just with the first part, we already would know finiteness of the number of ergodic measures of maximal entropy. So the goal here is then, okay, how even without transitivity can we still go to uniqueness? So just to recall a measure is Bernoulli if the system F mu is measurably conjugated to a Bernoulli shift. So the Bernoulli property is much stronger than ergodicity. So a first result is the following. There exists some parameter K0 such that for any parameter larger than this K0, the standard map Fk has a unique measure of maximal entropy, and this measure is Bernoulli. So, and also, actually, this proof is C2 robust, meaning that there exists a C2 neighborhood of the standard map Fk, such that any system in this neighborhood has at most one measure of maximal entropy. This does not talk about the existence of such measure, but what I say is that if such a measure exists, it's unique, and furthermore, it's also Bernoulli. So since as you change the parameter K that gets to a continuous family in the infinity topology of diffeomorphism, with the uniqueness, you can get the corollary that the map that takes K for K large enough to the measure of maximal entropy for Fk, this map is continuous. So it changes continuous with K. So another type of results that I get for the properties that I can get for the measure of maximal entropy is regarding active distribution of periodic points. But for this, I'm going to consider what is called the whole hyperbolic periodic point. So if you fix a positive number rho, this is the set of periodic points of period n. So this per n rho of f is the set of periodic points of period n, such that if you look at the derivative in the period of p, every eigenvalue has absolutely value larger than exponential to the rho n. So in particular, this is equivalent of saying that the Lyapunov exponents are have absolutely value larger than rho for this. And a second result is if you have K and U as before, so K large enough, and there is a C2 neighborhood of Fk U, such that if you look at any diffeomorphism in this neighborhood, which is also C infinity, well, since it's C infinity by Neuhaus, we know that there is a measure of maximal entropy. And since it's in U, we know that this measure is unique. So there is a unique measure of maximal entropy that I call mu G. And this measure has the following property. If you fix any number between 0 and the topological entropy of G, you get a growth rate control on the number of rho hyperbolic periodic points. So this is given by this equality here. So this is the exponential growth rate of the number of n rho hyperbolic periodic points. It's given exactly by the topological entropy. So for each n, this set of rho hyperbolic periodic points is finite. So you can also get this equidistribution result for this rho hyperbolic periodic points. So what you do is for each n, you average the direct mass on the rho hyperbolic periodic points, and then you divide by the number of points you're summing. So this, for each n, this is a probability measure. And what this says is that the sequence of probability measures has a limit as n goes to infinity, and this limit is the measure of maximum entropy. Another information that we can also get for this measure of maximum entropy is about how large it is. So in a first moment, about regarding its house of dimension. So the dimension of a measure is given, the house of dimension of a measure is given by this formula, which is you look at all the sets of full measure for this measure, and you look at the house of dimension of this set, and you take the infimum on all of that. So this is the house of dimension of the measure. And what we can get also is that for each epsilon positive fixed, there exists some K0, in this case depending on epsilon, such that for any K larger than this K0, the unique measure of maximal entropy verifies that the dimension, the Hausdorff dimension of this measure is larger than 2 minus epsilon. So this measure has Hausdorff dimension very close of being 2. And we also know that the support of the measure has density at least 8 over k to the 1/3. So it's also fairly spread out in the torus. And these two properties are C2 robust. Okay, and a last information we also get for the measure is when you look at generically large parameters. So there exists some K0 in a G delta dense subset in the semi-interval K0 to plus infinity, such that any parameter in this residual subset, the Hausdorff dimension of the support of the measure of maximum entropy is 2. So just to make a distinction, in the previous result, we talked about the Hausdorff dimension of the measure. In this result, it's about the Hausdorff dimension of the support of the measure, which oftentimes it's a larger number than the Hausdorff dimension of the measure. And for this particular result, we cannot say that it's we do not know. I do not know how to say that it's this estimate is C2 robust.
Davi, could you show us the previous slide again?
Yes.
Because I went a little quick. So this is the support. Okay, and the other one.
So here's the Hausdorff dimension of the measure, and I can say that it's larger than 2 minus epsilon. And in the next slide is for generic large parameters, and I can say that the Hausdorff dimension of the support is 2. So it's I'm looking at Hausdorff dimension of 2 different things, but yeah.
Thank you.
So this is just to give a list of the properties we can get for this measure of maximum entropy. And I'm gonna focus mostly on the proof of the uniqueness of the measure of maximum entropy. Depending on how I do in time, I will just say a few words about the equidistribution of rho hyperbolic periodic points. But just an overview of what's going to appear for the proof of uniqueness of the measure of maximum entropy for the standard map. There are 3 main ingredients that will appear. So first one is, okay, we need a criterion or something that will tell us, will give us a path of how to prove this uniqueness. And this criterion is given appears in the paper of Buzzi, Provisier, and Tariq. And the key word and a key definition here is something called homoclinic classes of hyperbolic measures, which I'm going to define. But this criterion is going to allow us to reduce the problem of proving uniqueness to a problem of finding transverse intersections between passing stable and unstable manifolds of hyperbolic measures. And that's the second step. So it's the key technical part that appears in the paper, because the rest I can import from other things. So it's how do we find homoclinic relations between measures, between hyperbolic measures with large Lyapunov exponents. And here large is going to mean a precise estimate on the Lyapunov exponent. And a third ingredient then comes from one of the estimates that appears in Duarte's paper, that we need to say that the topological entropy of the system is sufficiently large so that, and this large meaning some precise thing that I'm gonna say later, so that a measure of maximal entropy will have large Lyapunov exponents. So those are the 3 main things, and I'm gonna go through each of them throughout this talk. So first thing then is to state this criterion of uniqueness by Buzzi, Provisier, and Tariq. And for that, I need to define these homoclinic classes of hyperbolic measures. So just to recall, a hyperbolic measure, a hyperbolic measure is a measure such that almost every point has All the Lyapunov exponents for almost every point are non-zero. And as a notation, I'm gonna write this P ST of F as the hyperbolic measures of F of saddle type, which means that there will be one positive and one negative Lyapunov exponent for these measures. So the hyperbolic measures of saddle types will be the measures with one negative and one positive exponent. So just to recall on Pesin theory, if we have more regularity, for instance, F is C2, actually C1 plus alpha is enough, C1 plus holder is enough, and you have a hyperbolic measure of saddle type, well, you may, for each point X, you may look at those two sets, which is the stable and unstable manifold. So the W minus of X is the set of points Y, such that the future orbit of Y converges exponentially fast to the orbit of X, to the iterative, respective iterative of X. And similar thing for the unstable, but looking at the past. And Pesin tells us that when you have more regularity, almost every point these sets are actually immersed C1 curves, since I'm looking at saddle type hyperbolic measures, so with one negative and one positive exponent. And furthermore, you have on the point X, these curves are tangent to the Euclidean direction, which I write E minus X and E plus X. So I want to define homoclinic relations between hyperbolic measures. So it's a good thing to recall this definition first for hyperbolic periodic orbits. So given two hyperbolic periodic orbits, O and O prime, we say that O is smaller or equal than O prime if its stable manifold intersects transversely the unstable manifold of O prime. And I say that O and O prime are homoclinically related if O is smaller or equal than O prime and O prime is smaller or equal than O. And a picture is more or less like this. So you have unstable manifold of O. There could have some tangencies with the stable manifold of O. But there is at least some transverse intersection. And the same thing happens between the unstable manifold of O and the stable manifold of O prime. So if this happens, then you say that O and O prime are homoclinically related. And the homoclinic class of a hyperbolic periodic orbit is defined as the closure of the set of all the hyperbolic periodic orbits that are homoclinically related with O. So the idea now is to do the same thing, but with measures and changing the stable and unstable manifolds to stable and unstable Pesin manifolds. And so given two saddle type measures, mu1 and mu2, we say that mu1 is smaller or equal than mu2 if you have the following. If there exist two sets, each of which have positive measure, so lambda 1, lambda 2, each of which have positive measure for mu1 and mu2 respectively, such that for any pair of points in the product of these sets, the passing stable manifold of one intersects transversely the passing unstable manifold of the other. And similarly as before, I say that these two measures are homoclinically related if mu1 is smaller or equal than mu2, and mu2 is smaller or equal than mu1. And this is not a very good picture, but it's just something to have in mind. So now you have some sets that have some meaning for each of these measures. So lambda 1, which has mu1 measured positive, and lambda 2, which has mu2 measured positive. And you get some transverse intersection between the stable and unstable manifolds of each. And the key definition then is this measured homoclinic class of a hyperbolic measure. So the measured homoclinic class of a hyperbolic measure mu is defined as the set of all the other, so mu here I'm supposing is a saddle type measure. So it's the set of all the other saddle type measures nu that are homoclinically related with mu. So the measured homoclinic class of a hyperbolic measure is something that lives in the space of probability measures. And you just look, given a hyperbolic measure, you just look at all the other measures that are homoclinically related to it. So this is something that lives in the space of probability measures. And the criterion that appears in Buzzi, Crovizet, Sarik's paper is the following. For any R larger than 1, if you have a CR surface diffeomorphism, and then you suppose that you have a measure of maximal entropy, an ergodic measure of maximal entropy, then this measure is the unique measure of maximal entropy in the measured homoclinic class of mu. So once again, in other words, what this theorem says is that there are no two measures of maximal entropy that are homoclinically related. There are no two different measures of maximal entropy that are homoclinically related. So inside a measured homoclinic class of a measure of maximal entropy, this measure is unique. And what is behind this result is it's also this coding type of techniques that Yuri explained in his talk. And this result actually can hold in higher dimension. Oh, holds in higher dimension. And you just need a C1 plus order here. So, okay, so with this criterion, then the goal is the following. We want to say that for a large parameter K, any two measures of maximal entropy are homoclinically related. So by the criterion, they will have to be the same, and that would give the uniqueness. And the main difficulty that appears here is, again, you want to find transverse intersections between testing stable and unstable manifolds. But these objects, the length of these manifolds and its geometry and also the Ozella-Betz directions, this change only measurably with the base point. So in a certain way, what you're looking for is some type of quantified version of Bézin theory. So the key theorem here then is something that about finding homoclinically relations between measures. So for that, I fix some scale, delta equals to 1/600. This is not optimal, but it worked for me. And the key theorem is the following. There exists some K0. Actually, here it's R, doesn't have to be natural. So there exists some K0 such that for any K larger than this K0, the following holds true. For any two saddle type measures, ergodic saddle type measures, whose absolute value of the Lyapunov exponents are larger than 1 minus delta log K. So this is what I mean by large exponent. It has to be larger than this 1 minus delta log K. Then any two such measures are homoclinically related. So in other words, we can find these transverse intersections as long as the Lyapunov exponent is large enough. And by large, I have some precise estimate here, 1 minus delta log K. So this is the second ingredient. And a third ingredient then is, okay, how do we get this estimate for the measure of maximal entropy? And that appears in, so just a comment on that, is that, so you have these REL inequalities tell us that the entropy of the measure, in this case, our measure is saddle type, so the entropy of the measure is bounded from above by the positive Lyapunov exponent. And if you may also look in a similar thing for the past with minus the negative Lyapunov exponent. So in particular, if you know that the entropy of the measure is large, then you get that the Lyapunov exponent is also large. So now what we're looking at is to say that the entropy of the measure of maximal entropy is large, and this is equivalent of saying that the topological entropy of the system is large. So this appears in Duarte's paper. So there exists some K0, some parameter K0, such that for any parameter K larger than this K0, well, there exists some set, some compact set lambda K, which is a transitive, locally maximal, uniformly hyperbolic set, such that Fk restricted to lambda K, so the dynamics on this compact invariant set lambda K, is topologically conjugated to the full shift of 2 and K symbols. And so we know that for the full shift, the topological entropy is given by log 2 and K. So here, there's also an estimate of how this number grows, and it's the following: the limit as K goes to infinity of 2 and K over 4K equals to 1. Actually, in the paper, he gets some precise lower bound of the number 2 and K, depending on K. But just with this, if K is large enough, we can guarantee that the topological entropy is also large. And by large, I mean verifying the inequality that I showed in the previous slide. So a corollary is that there exists some K0, such that for K large enough, K larger than this K0, the topological entropy of Fk is larger than 1 minus delta log K. Now, if we put those three pieces together, it's not hard to conclude the uniqueness. So just to recall the ingredients that we had this criterion of uniqueness by Buzzi, Crozier, Sarig, and this criterion allows us to reduce the proof of proving the uniqueness into proving that any two measures of maximal entropy are homoclinically related. Then you have this key theorem that states that any two ergodic measures with large Lyapunov exponents, so here large, just to recall again, is that the absolutely value is greater than 1 minus delta log K. So any two such measures are homoclinically related. And the third point tells us that measures of maximal entropy have large exponents in this quantitative way. So by Duarte's estimate, we would know that any two measures of maximal entropy will have large Lyapunov exponents. In particular, they will have to be homoclinically related. And by the criterion, this implies that they would actually be the same, and you get uniqueness. So the ingredient easily implies the uniqueness. So I'm gonna give the main ideas of what appears in the key theorem. So how to find these transverse intersections. And so there is a local strategy and a global strategy. And these strategies, they are the ones that also appear in the proof of stable ergodicity for the Bejertares, for example. So the local strategy is based on the following theorem by Crozier and Pujals. So it's a technical theorem which states the following. So if you have a C2 surface diffeomorphism, and you have four quantities, sigma, sigma tilde, rho, rho tilde, between 0 and 1, they verify some relation, some numerical condition between them. So for any point in your surface having some direction, E, that verifies the following. For any non-negative N, you see contraction, you see some control contraction in the direction E, that's given in this left side. So from above, it's controlled by sigma to the N, and from below, it's controlled by sigma tilde. So this is a contraction hypothesis, contractual condition, and you have a dominated domination type of condition, which is given by this one. So you take the determinant, the Jacobian of the Fn on the bottom, and you square the contraction you see on the top. And again, you have control from above and from below on this expression. So here, for any point having a direction that verifies these two conditions, well, this point has a stable manifold tangent to this direction of uniform size, and the size only depends on the constants that appeared and on the C2 norm of S. There are no measure involved. There are no invariant measure involved. It's a theorem that applies to any point having a direction that verifies this. So the idea now then is to look at the standard map, look at a measure of maximal entropy or measure with large Lyapunov exponent, and the largeness of the Lyapunov exponent will come so that this type of condition would hold as we put the appropriate sigma, sigma tilde, rho, and rho tilde. And to try to apply this construction of stable manifolds in this setting. So again, we need to find points with directions that contract and with some domination. So now, suppose we have two saddle type hyperbolic measures with large Lyapunov exponents. So the exponent is larger than 1 minus delta log k. So the strategy comes through using Fleet's lemma. I'm not gonna give the precise statement of Fleet's lemma, but Fleet's lemma allows us to find these points with what I call hyperbolic times. So points that we will see the contraction for every n on that moment on. And just a comment on this. So if we, in our setting, if we find points having a direction that verifies this first condition here, the contraction on the direction is controlled by sigma and sigma tilde. The second condition comes for free because the determinant is 1. So you just square anything that you obtain on this left inequalities, you just square it and you obtain this right inequality. And here will be exactly the points with the Fleet points with hyperbolic time, as you apply it for the oscilla that's stable and unstable for the past direction. So this Fleet's lemma is going to allow us to obtain good points for which we can apply the construction. Now, once we can apply the construction for these points, we just start following everything, all the steps of the construction as precise as you can to obtain precise estimates, and we can obtain the estimates that actually, for these points, these good points that we can apply Fleet's lemma, that we obtain by applying Fleet's lemma, the stable and unstable manifolds for these points are large. They are larger than k to the minus 7, so you obtain some precise size. And you also have some control on their geometry, meaning they are tangent to certain cones in your manifold. So in this local picture, what you have is something like this. You have those two measures with large Lyapunov exponents, and you obtain those sets coming by applying Fleet's lemma, such that for points in these sets, they're gonna have some good stable and unstable manifolds, with length larger than k to the minus 7. So this is good to give us some control, but it's still not enough because just with this k to the minus 7 estimate, we cannot guarantee that these manifolds are gonna intersect transversely. So now we need to say something to obtain the, there is a global strategy that we need to apply to be able to mix those two manifolds together to find these transverse intersections. And that actually comes with the following ingredients. So Fleet's lemma not only gives us the existence of good points, but it also gives us an estimate on the measure of these good points. So we can obtain from this lemma an estimate on the measure of the set of good points where we have good stable and unstable manifolds. And actually, if K is large, this set has large measure. And since this set has the set of good points has large measure, and with precise estimates that comes from the example, we can say that many of these points, of these good points, are going to spend a long time inside the hyperbolic region. And if they spend a long time inside the hyperbolic region, you may hope that the stable manifolds and stable manifolds are going to grow to something global. And that's exactly what happens. We can say that these manifolds that are small, but with a uniform size, they grow to become something global in the torus. So a rough picture is like this. So you had the point P0. This is a good point for mu1 that spends a good amount of time in the hyperbolic region. So as you iterate the unstable manifold, which in this case is going to be an almost horizontal curve, is going to start to grow, and eventually is going to grow in a way that it crosses the torus in the x direction, let's say at least twice. And I can say for the specifics of the example that this happens in a time not higher than 15. And then you look at the point Q0, which is a good point for mu2 that spends some time in the hyperbolic region for the past. And you look at the manifold, which was small at first, and you start to interact with for the past, and eventually become something global. So it's going to become an almost vertical curve that crosses the y direction. So this will force those two curves to intersect transversely. And this picture is actually gives some idea, but it's actually a bit deceiving because it gives the idea that we can control that this happens for the entire unstable manifold of P0 and for the entire stable manifold of T0. And actually, that's not quite true. A more accurate picture would be the following. There is some subinterval in the unstable manifold of T0 such that in iterate N1, it's going to cross in this way. So it's not necessarily, you don't control necessarily the entire unstable manifold of T0, but you can find some good intervals that are going to be very large in the x direction and almost horizontal. And the same thing for the past in the stable manifold of Q0. There is some interval inside the stable manifold such that as you iterate this interval to the past, it's going to grow to something global like this. And that gives you the transverse intersection. So just to summarize, what the pictures are saying is that this control on the measure of the set of good points for on the set of good points that for these measures with large exponents allow us to find that many of such good points are going to spend a long time in the hyperbolic regions. And since they spend a long time in the hyperbolic regions, their unstable stable manifolds are going to grow. Part of their stable and unstable manifolds are going to grow in a way that they're going to have to intersect transversely. So these two ingredients, they are going to give us the homoclinically relation between measures with largely Lyapunov exponents. Just a few comments on the proof. The estimates we obtained for this proof are C2 robust. That's why we get the C2 robustness of the system. The Bernoulli property also comes. I didn't state the full criterion that appears in Bouzy-Crovisier-Saric's paper, but there's also another part that describes that the measure of maximum entropy has some period, such that in the period there is a decomposition in some period, such that each measure in this decomposition in the period is Bernoulli. So essentially, what you do is that you show that this decomposition is only one, and it comes from the same type of techniques. And okay, so Since the estimates we obtain are C2 robust, so the same strategy applies. And what you can obtain is that C2 robustly for Fk, there is at most one measure of maximal entropy. However, as I mentioned in the beginning, we do not obtain the existence of measure of maximal entropy C2 robustly. We know for Fk because it's infinity, so we can apply Newhouse theorem. But if you allow finite regularity, we don't know. So actually, I conjecture that for k large enough, there exists a measure of maximal entropy C2 robustly. So there exists a measure, and this measure is unique by the theorem, but C2 robustly that it happens. And this conjecture is actually supported by another conjecture that appears in Buzzi-Crovizet-Sarig's paper, where for finite regularity, they conjecture that a CR surface diffeomorphism F, whose topological entropy is large enough, so the topological entropy is larger than log of the Lipschitz constant of F over R, has a measure of maximum entropy. To be more precise, their conjecture is not exactly with the inequality here being log of the Lipschitz constant of F. It's something that could be slightly weaker, but this is enough to simplify the presentation. And the thing here is that Jérôme Buzzi, he has examples of systems with no measure of maximal entropy, with finite regularity, but having the opposite inequality, but their entropy is small in this sense. And for the standard math, if k is large enough, the system is going to verify this for R equals 2. So I had a few things, a few comments about the equidistribution, but I'm just gonna skip them actually, so since I don't have too much time. I wanted to finish with a few questions that appear with this work. So a first question is, can we say something more about this measure of maximal entropy regarding exponential decay of correlation? So this proof does not give the exponential decay of correlation. Can we say that the measure of maximum entropy has exponential decay of correlation? Another question is, so I mentioned that for k large enough, the map that takes k to the measure of maximal entropy for Fk, this is a continuous map. So maybe you can wonder about the regularity of this map. So you may fix some metric on the space of probability measure, and you may wonder, and you may try to say something more about the regularity of this map if it's older, if it's, I don't know. It's not very precise, this question, but yeah, maybe some more information about the regularity of this map. So you may look also at the map that takes k and sends to the positive Lyapunov exponent of the measure of maximum entropy. Can we say something about the regularity of this map? So we don't know if this is even continuous, so can we say something about this? If this is continuous or even more regular? Maybe in some intervals, I don't know. Another question. Okay, so we know, but actually by Newhouse paper, it's also proved that since this is a family of infinity, it's a continuous family of infinity diffeomorphisms in this infinite topology. We know that the topological entropy with respect to the parameter k, it's a continuous function. We also know that as k goes to infinity, the topological entropy is going to go to infinity, so it's going to grow. But can we say something more about the behavior of this function? I mean, is it strictly increasing? Are there moments that it's constant? Are there moments that it drops a little bit and then grows? Can we say something about these moments or the dynamics of the standard map in these moments? Yeah, so can we say something more about the behavior of this function that takes k to the topological entropy of Fk? And Okay, so I mentioned that one of the properties that I obtain is that for every atom, if K is large enough, then the Hausdorff dimension of the measure of maximal entropy, it's larger than 2 minus epsilon. So it gets close to 2. However, is it true that it never reached 2? Is it true that the Hausdorff dimension of the measure of maximal entropy is strictly less than 2? Just to say a few words on that, if the measure of maximal entropy had its Hausdorff dimension equals to 2, then a combination of Le-Drapier-Young's formula with some dimension formula also from Lysen-Young would actually imply that the measure of maximal entropy would be an SRB measure if the Hausdorff dimension was 2. If this was true and you are in a volume preserving setting, that would imply that the measure of maximal entropy is absolutely continuous with respect to the Lebesgue measure. And this does not usually happen and is usually in very, very rigid scenarios. So I would be extremely surprised if for some large parameter K, the measure of maximal entropy would be absolutely continuous with respect to the Lebesgue measure, but we also don't know how to prove that it is not. So, and just a last comment is that this type of technique, if we suppose that finite conjecture is true, that the standard map for large parameter has positively Lyapunov exponent, in the conjecture is also there is also a lower bound on the entropy that is hoped. If this is the case, I also believe that some of these techniques could be applied to give an upper bound on the number of ergodic components in the hyperbolic region of the volume. Supposing, of course, if the conjecture is true and you get the good estimates for the entropy, then this type of technique could also be used to give you some upper bound on the number of ergodic components for the SRB measure, or for the hyperbolic region of the Lebesgue measure. So I'll stop here. Thank you for your attention.
Okay. Thanks, David, for the presentation. Are there any questions?
I have a question.
Yes.
Hello, Daisy. I have a simple question for the general topological behavior of the dynamics for large K. So can we expect something of this kind to be true, like in the chaotic region, chaotic C outside the elliptic islands, is the dynamics transitive? Like I think of results by Le Calvez, Fabio Tal, Martin Sambarino. They show some kind of that the heteroclinic classes are rich, right? They cover a lot of space. Mm-hmm. So can you expect something like transitivity outside the elliptic islands?
So I think that's a good question. Actually, I didn't mention, but you obtain a little bit more. You can obtain that the support of the measure of maximal entropy coincides with a homoclinic class of a hyperbolic periodic point. And we also, and the question is this everything outside the elliptic island? I don't know. It would be interesting if it was. But you know that there is a topologically transitive set that will capture the information for the measure of maximal entropy.
So we can even believe that even for small k, for k in the km region, maybe inside the Birkhoff regions between two invariant curves, we still have this kind of transitivity outside the elliptic islands.
Okay.
So do you expect like unicity of the maximal entropy measure even for small epsilon, even for small coupling?
That I don't expect that much. I think there could appear many regions with. Oh yeah, that's what you said.
Well, if it is transitive outside the elliptic islands, so inside each Birkhoff region, there will be only one maximal entropy, and they have no reason to be equal, right? There is countably many. I don't know.
That's a good question. I don't know what to expect for a small parameter.
So what fails in the small parameter? If I understand in your proof, to go from 1 over K7 to 4 for the size of the stable and unstable leaves, a manifold, you just apply like a pigeonhole principle, something like this, right? You have a big measure set of the peasant set and the big measure set of the good region. So there exist long segments of time inside the good region.
Yeah, so pretty much, actually, it's you can take advantage of the specifics of the standard map to say that you only have information about the center point, the P0, P1, P2 that is in the good region, and you know that you have this connected curve that contains this point. So I actually use 2 different good regions and 2 different bad regions. And I know that if the curve doesn't grow completely, and that's something like this, it must intersect the boundary of these 2 bad regions. And for the specifics of the map, I can say that once it intersects the boundary of these 2 bad regions, after one iterate, the segment that intersects will have to grow in some large size like this. So yeah, you can think of as some pigeonhole principle in a certain way.
Okay, and all this collapses for a small coupling because
yeah, that's true.
The entropy you expect is double exponentially small in the coupling.
And also I need the yeah, it's very important that I need that the entropy to be large enough to apply this technique. So it's very important for me that the entropy it's almost log K.
Okay, but just a final question, last question for me. If you had transitivity outside the elliptic islands, then the result of Crovizier, Buzy-Crovizier, and Sarig would imply uniqueness of the maximal entropy, right?
If you knew that the entropy inside the elliptic islands is strictly less than
of course.
Yeah, I think so.
Okay, thanks.
There are more questions?
David?
Yeah.
In the proof of exactly in the moment of this picture, just before you say that you need also a control of the geometry of the invariant manifold. Could you explain a few words about how you control the geometry?
No, yeah, actually, because what I obtain with the construction is that for instance, the unstable manifold is not only has a size larger than k to the minus 7, but I also can say that it's tangent to some horizontal cone. And that's what I mean by geometry, with some specific estimate of this horizontal cone. Because again, it's not only about these curves being large, but it's also about these curves being large in the good direction so that you get transversality. So you think in this picture, you think of horizontal cones as being expanding direction and vertical cones as being expanding for the path. So is this type of geometry control that I mean. Is the stable manifold is tangent to some vertical cone, the unstable manifold is tangent to some horizontal cone. And that's what allows you to, okay, after you iterate a few times, this has to grow to some large size and also to get this picture, some large size and also horizontal, and some large size and also vertical.
And this is also use the specifics of the map, or is something more general in this part?
No, yeah, this is just the specifics of the map.
Okay, thank you very much.
More questions?
Can I ask you? Hello, David. Can I ask you a comment? So there are these classical questions or conjectures. I've learned it from Lennart Carlson and Michael Benedicts. For instance, they expected that for many parameters there would be no elliptic islands at all. Or even if there are always elliptic islands, this is also a very hard question. Maybe the total area of occupied by these KM structures of these elliptic islands should be relatively small in the phase space. So I was expecting that your measure of maximal entropy would be absolutely continuous with respect to the area, to the Lebesgue measure. But you are pointing in the, as I understood in the end, when you were making these conjectures, you were pointing exactly on the opposite direction. Can you comment on this and why do you expect this?
The last one is actually not a conjecture, it's a question. So I don't.
Okay.
No, sorry, but measures of maximal entropy tend to be singular. That's a fact. It's how it should be. So, and by the way, if you expect the measure of maximal entropy to be absolutely continuous, it means you found the positive entropy for the, which is a very, very hard problem.
Yeah. So like Batson said, it's usually very rigid scenarios that you have the measure of maximal entropy to be absolutely continuous. So for this reason, I don't expect it.
Okay.
But as I said here, if I make a question, I don't make a conjecture. But just one comment in what you said. Actually, I didn't mention, but the result of Jacopo-Simoy actually goes in the direction of some of the comments you made. He analyzed a specific type of elliptic island that he calls one cyclicity. It's more or less, if I understand correctly, it's some elliptic island that passes only once in this critical region. And what he proves is more or less this. He says that there is generically there are infinitely many elliptic islands of this type for large parameters, but in a set of full measure there is only finitely many. So it's if I'm not making a wrong statement here, I think that there was this result, and it goes in this direction of what you said. That for many parameters, you wouldn't have elliptic islands or not many elliptic islands, but generically you still get them.
I knew this kind of results, but okay, these are only a small fraction of all the elliptic islands that could be playing around.
Yeah.
Yeah. Thank you very much for your very nice talk.
Thank you.
Are there any more questions? Well, thanks again, David, for the great talk. Next week there is a talk by Rafael Potri. Well, I don't know if Lorenzo wants to say something.